All right, it's recording. Okay. Okay. All right, you ready? Okay, I put it recording, and I'll just check a little bit a few times through to make sure there's nobody in the waiting room. So, all right, this is the Michigan Technological University MTU Facilities Pathway Project. We are Joe Engineering. We are Group 1, and we were responsible for pathway structure design and geometric layout. Following the conclusion of this presentation, there will be a presentation on the pathway regarding construction and geotech, and then Group 3 will be talking about environmental / stormwater in regards to this pathway. My name is Owen Matala. I was responsible for the structural design for this part of the project.
My name was Eric Peterson. I was responsible for the pavement design and the construction schedule.
And I'm Jake Paquette.
Okay. I think all not going to use one, but okay. 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 Sorry for those technical difficulties. We are ready to go now. So a little outline of this presentation today. We're going to talk about the background, some existing conditions, the geometric layout of the pathway, the retaining wall design, pathway surface design, a construction estimate, a construction schedule, and then some of our conclusions and recommendations from the semester. So for project location and background, there is currently limited access between upper and lower areas of campus. In this picture on the right, you can see the trees, these pine trees, and the upper highway there is Cliff Drive, and the bottom road is Phoenix Drive. And in order to traverse these parts of campus, currently the use of a vehicle or using a building or elevator is required. And again, this pathway is located west of the Dow Environmental Sciences Engineering Building. And the goal of this project really looks to improve the accessibility of campus. So the required project scope for Joe Engineering was pathway geometric design and layout and alignment, some cut and fill calculations, structural design of retaining walls, pathway surface evaluation and design. And then we also made sure all our design followed state and federal highway standards. And then some client requests: provide safe bicycle travel and pedestrian travel, a pathway slope of less than 10%, 10-foot path required for snow removal and maintenance equipment. And then the design has to fit into current campus aesthetics.
Here's a few of the existing conditions. We had this hillside slope at 26 degrees, but it was steeper in some spots. Down on the west side, because there were some hills, 75-foot elevation change between Cliff and Phoenix. The canal was 10 to 12 feet below Phoenix, so we didn't have to worry about the water table. The hillside contains mature trees, 40 to 50 years old, and all the soils are boulders, gravel, sands. Here's the existing utilities. The majority of them are on the hillside, besides the sanitary, which is the pinkish you can see going down, and then the green is the steam tunnel. The one that's more shaded is the existing or the current one, and the one more west is the abandoned one. So here's our horizontal alignment. We tried doing a switchback, but quickly realized there just wasn't enough room between Cliff and Phoenix laterally. So we ended up with a straight path. It's all the way down. There's a vertical alignment. As you can see, we have that -9.88%, right under the max of 10. And then the shaded regions are max cut and fill at each spot. We had to cut around 21,000 cubic yards and fill around 4,500. Here's a 3D view of our path. So on the bottom, you can see that's Phoenix, top is Cliff Drive. And those are those 3 hills I was talking about. This is why we have a major cut. Our path basically has to go right through some huge, big maybe rock faces, and that's why it's so steep. But we're not sure.
So in terms of cutting through this hillside, there's 2 types of retaining walls that we concluded on recommending. For areas where there is cut, we have decided there will be a soil nail wall, and we're fill an MSE wall. But before that, we did a retaining wall evaluation. And on this list is obviously soil nails and MSE wall. But we ruled out sheet pile because of the rocky cobble soil conditions. It would have been very difficult to dry pile in these. A cast in place gravity wall we also evaluated. While there will be a cast in place facing on our soil nail wall, a cast in place gravity wall would have to be much thicker. And additionally, it is one of the most expensive retaining wall options. And then soldier pile and lagging, again, that may be somewhat difficult with the existing soil conditions. And again, that would require another facing because of in order to fit into campus aesthetics. So first of all, I'll talk a little bit about the soil nail wall design. For this area, for the pathway, it will be approximately 400 feet long. And just some advantages of the soil nail wall after our evaluation. They are relatively easy to construct, and they can be constructed quite quickly. It requires a lot smaller equipment compared to other retaining wall methods. The nail angle and location can be adjusted very easily if underground obstructions are encountered or boulders such as that. So here is the soil nail main components. Everything you see here in this picture we did design. And I will just talk a little bit about that there is an initial facing, which is what the soil nail is actually attached to. And it that is a shotcrete facing. And then the permanent facing is a cast in place 8-inch facing. So we utilize the design hollow bar soil nails, and with these soil nails, the grout is injected through the center of the bar during drilling. And the hollow bar method does prevent hole collapse during drilling, and we think this is definitely a better idea just because the soil conditions may not be favorable for solid soil nails. And then these soil nails are tension elements that reinforce the soil. Again, because we are performing such a big cut through the hillside, there is a need to support this soil. So here is a final sketch of the soil nail wall. It will be constructed in 3 vertical stages of construction at 5 feet each. Now, it has to be done in 3 stages because the soil does not have adequate stand up. It will not stand up by itself, cut 15 feet high. So again, and then that 5-degree batter just is an additional factor of safety that allows for the little bit easier installation of the nails. Here is just a little view of the soil nail wall with the welded wire mesh and the bearing plates and headed studs. And on the right here is a completed soil nail prior to the permanent facing being attached. So just a few final design specifics. Again, the wall length will be 400 feet. The wall height is an average of 15 feet and 6-inch shotcrete facing, 8-inch permanent cast in place facing, and nail inclination of 15 degrees. And all these follow Federal Highway Administration factors of safety and design guidelines. Now, for the other wall where fill is required, we recommend the use of a MSE wall. It'll be approximately the top 250 feet of the path. Due to time constraints, we did not complete a formal design, but we have presented our recommendations regarding MSE walls in our report.
Yeah, so here's a drawing just showing where the retaining walls are actually going to be. As Owen said, the top 250 feet or so will be the MSE wall. Then there'll be about 100 feet or so of nothing. And then the bottom 400 feet or so will be the soil wall. So here's just a typical cross section of the soil nail wall. As you can see on that left side, 15 feet high on a 5-degree angle, with a 2-to-1 slope on either side. And then a typical section of the MSE wall. If the MSE wall is 15 feet tall, and like I said, the top 250 feet will look like this.
For the subgrade design, prior to construction, it requires to be remove all vegetation, minimum 5 feet outside of the trail. And then cut the grade or cut the slope to grade and compact to a minimum 95% standard Proctor density. And the moisture should be within 3% of optimum. And a 3/4 inch aggregate base course is used, and that also should be compacted to a minimum of 95%. The life cycle cost analysis for the 3 materials we considered for this project, they were asphalt, concrete, and brick pavers. The initial cost was found by taking the cost per square foot of the material and dividing that by, or multiplying that by the square foot of the project. And the cost per year was found by taking the cost per maintenance for maintenance on the material and multiplying that by the square footage. And at year 20, asphalt requires a complete replacement. So those costs were factored in at year 20. And for concrete at year 25, it also requires a complete replacement. And so looking at that, we decided asphalt was the best option for this project, being that it came out to be the cheapest. The pavement design, we decided to go with a Marshall mixture 36A. That's the table on the far right. This is with the 3/8 inch aggregate with 4% air voids and a 16% DMA and asphalt binder content of 95 or 5% and aggregate of 95%. For the thickness of the pavement, we based it off the thickness guidelines from the National Asphalt Pavement Association. As you can see, it's based on the table, we classify it as a high quality soil with a medium loading on the path, which requires it to be about a 3 to 3.5 inch thick pavement. And for the AASHTO soil classification table down at the bottom, it requires us to have about a 2.5 inch thick pavement with 4 inch aggregate base. For the design, we decided 3 inches was a good medium and an aggregate base of 4 inches. And a few additives we consider to add would be sand seal, which being that the slope is so steep, this fills fine cracks and makes the pavement more durable and increases the traction. And for rubber, that just increases the pavement life by lessening brittleness and cracking.
Here's just a section of the path. As you can see, we have our two 1.5-inch asphalt lifts, 4-inch A base, and then the 6-inch sub base. You can see we have both handrails on both sides, 34 inches tall. There will be a gutter or a guardrail on the north side. It's just not shown here. And then obviously, soil mill wall will be right up against this handrail, and then MSC will be right off this gutter. So our major cost items, excavation was our biggest cost with that 21,000 dirt cut. Soil mill components following behind, and then the MSC wall, and then the backfill, the 4,500 dirt backfill that we had. Here's a breakdown of our total estimate with the soil mill wall components together, came up to be the most. And that's at 503,000, earthwork 465,000, the MSC wall 156,000, pavement 33,000, the incidentals 80,000, and then we have contingency of 261,000. That all came up to be 1,571,000.
Yeah, I'd just like to add a little bit about the high contingency. Now, we believe there may be significant rock located within the area, and this high value contingency of roughly 16 to 17% is just to ensure that this is adequately priced. We believe that we would require some more soil borings within the pathway extents to verify if there is rock contained in the soil or not.
For our construction schedule, we utilized the RS means and the MDOT roadway and bridge production rates from 2018. We took the item quantity and divided it by the MDOT daily production rate that was used to obtain a duration in days. And we did the same for RS means daily output. And we're assuming a 5-day work week and an 8-hour work day. Here's our major project durations. We have mobilization for a duration of 6 days, earthwork 14 days, and the soil mill wall 35 days, MSC wall for 9.5, pavement for 2.5, and the incidental construction for 10. A little bit about this is as Owen mentioned earlier before, we have earthwork and soil mill wall divided into 3 phases due to required vertical construction. So it requires 5 days of earthwork, 3 days of earthwork, and 5 days the soil mill wall, and that is repeated for 3 phases. And this results in a total project duration of 95 days with the 8-hour work days and 5-day work weeks.
And again, these estimates and schedules are just for Joe Engineering's portion of the work. We have come up with a total price and total project duration that I can discuss further if anyone would like.
For the critical path of our project, due to the project being in sort of a small area, we figure most of the schedule is critical. We're assuming 1-man crew for this project, and due to the critical nature, the float is around 0.
So a little conclusion and recommendations to just wrap up the presentation. The straight path alignment is the best due to the limited access between Cliff and Phoenix Drive. A switchback design was not able to fit within this proposed area. The straight path does have some advantages though. It allows for easier snow removal, and it limits blind spots and keeps pedestrians somewhat safer. The soil nail wall design is a cost-effective and less specialized retaining wall option than others that we evaluated. An asphalt surface was determined on a life cycle cost analysis, and this cost analysis included initial cost, durability, maintenance, and the total replacement costs. And then a few recommendations for future work. We should verify the depths of the underground utilities. There were some discrepancies between actual depths and how deep they actually were. So we would recommend that to be verified. Again, as I mentioned, additional soil boring should be performed within the pathway extents. Prior soil borings from the 1995 construction of the Dow building were utilized. But again, they are approximately 300 feet away from where the path will be located. So we recommend further evaluation of that. And then where fill is required, we recommend the MSE wall. Again, we did not do a formal design, but we recommend that this should be evaluated further, and a formal design will be required of that wall. Thank you for your time, and we appreciate you joining us today. Are there any questions?
Thanks.
Yeah, I'm just curious, can you show me the entire project budget and schedule you put together? Do you have that in?
Yeah, so I do not have a slide, but the total project budget with the soil nail wall and MSE wall would be approximately 1.8 million. Yep. And then total schedule would be about a little over 3.5 months.
Okay.
So-
And the difference between your project estimate and total is because of the water drainage?
Yeah, so a little bit of the construction, just signage and kind of mobilization costs, they also picked up a little bit. And then, yes, the environmental stormwater, which was about 130,000. So,
Okay, yeah, nice job.
yeah, thank you.
I got one question. But it's, we talked about this a little bit, but can you say some more about what the expected footprint is again? I know we talked about the tree removal.
Yeah, so tree removal is a kind of a big deal here with this project. Quite a bit of the hillside, probably, Jake, what would you say, how many acres?
Well,
Probably 5-ish acres of the 7.
no, I think it is 2.8 total.
Oh, yes.
In reality, I would say at least acre of tree would probably go to get all the equipment through. I don't know. It's hard to say. It might be easier to just cut and replant. We didn't dive into that.
Or just get, I just wanted to feel like there's a.
Right.
Size.
Yeah, it's probably, so it's 2.8. I mean, it'd be easiest just cut them all down and then replant, but it's probably more like an acre.
So it depends on how much you want to grade the hillside. If you want to grade the hillside less, you probably would have to cut less trees, but then you end up with a taller wall, which is going to get significantly pricier, very quickly. So it's kind of a trade-off in terms of, how, because you could grade the hillside slightly less and you could make a 20-foot wall instead of a 15-foot wall. We pick 2-to-1 slope because that's what some areas already are on the hillside. So, that would allow somewhat of an easy tie-in. But that should be probably evaluated a little bit more. We did recommend that in the report, just to try to maybe analyze that a little bit more to see what the optimum slope of grading that is.
So in some ways, you might be better off just cutting all the trees, taking all the trees out, regrading the whole thing.
Yes.
But I think that would probably save time doing it that way.
Okay. Thoughts?
Any other questions?
So,
Okay. All right.